Okay, this will be the last of this current unit on chemical equations, classifying chemical reactions. Remember to copy all of this into your notebook and use the space bar to stop and start as needed. All right, these are the 5 types of chemical reactions we'll be looking at. These visuals here are really quite cute. They right now won't make as much sense as they will when you're done with the notes here. When you're all done with the notes, come back and look at these. You'll see that they're pretty cute and even a effective way of remembering the difference between the 5 types. Okay, so let's look at the first one, synthesis. A synthesis, also known as a combination reaction. For a synthesis reaction, a compound is produced from simpler substances, usually elements. Okay, so this is just a generic representation of that. So you can see that you have 2 compounds or 2 elements or an element and a compound, but they all come together to form one product. And that's the key that it's a synthesis reaction, is that you only have one product. You don't have a product and something else like you've seen in other reactions, just one product. So that's why it's called a combination. They come together to form one thing. Synthesis just is another way of saying to make something. Okay, so let's look at an example. Okay, so what you'll need to be able to do, if you're given the product, you need to determine what the reactants would be and the balanced equation. And all you need to do is look to see what the compound is made up of. It's made up of sodium and chlorine. So those are our 2 reactants. Sodium, we know, is a solid, and chlorine, we know, is a diatomic gas. So you simply write those down and then balance the equation. 2 chlorines, so we need a 2 here, which gives us 2 sodiums here, and that would be our balanced equation. Okay, so let's look at this actual reaction taking place.
Sodium and chlorine are examples of atoms that combine ionically. Sodium is a reactive, soft, silvery metal of low density. Its atoms have 1 valence electron. Chlorine is a corrosive, yellowish-green gas. Its atoms have 7 valence electrons. When mixed, the 2 atoms combine explosively as an electron moves from each sodium to each chlorine atom. A closer look at the resulting product reveals the formation of small white sodium chloride particles, also known as table salt.
Okay, so you can see, this is a good example, that in a chemical reaction, what you end up, the products are completely different from the reactants. Sodium and chlorine are very, very dangerous, very, very different. But when they come together, it makes just regular table salt. Okay, so let's look at another. Okay, so we're going to stop the video and see if you can do this one yourself. So the product is aluminum bromide. So what would the reactants be, and including the correct states, phases, and writing a balanced equation. So give it a shot. Okay, so here it goes. So we have aluminum, we know it's a solid, and we know that bromine is a diatomic liquid. Remember, there's only 2 liquids, bromine and mercury, on the periodic table. Okay, so we have 2 bromines here, 3 bromines here. So think a least common multiple of 6. So if we have 3 bromines molecules, that would give us 6 bromine atoms. So over here, we need to put a 2 to give us 6 bromine atoms, which means we need a 2 here, and that would be a balanced reaction. Okay, so let's look at this reaction.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
Okay, let me point something out here. At the very beginning, you can see that the beaker is filled with kind of a brown gas. Well, that's bromine. Bromine has kind of an orange-brown color. At room temperature, it's a liquid, but it's very volatile, just a little above room temperature, and it starts to vaporize. So what you're seeing, that orange brown gas that's being given off, is not the aluminum bromide. It's simply the bromine, liquid bromine, that's getting hot, and so it turns into a vapor. Okay, next, decomposition or analysis reaction. Now it's exactly the opposite of a synthesis reaction. Instead of having one product, we have one reactant. So it's a compound is broken down into simpler substances, usually elements. So we have one reactant and it breaks apart. Now the reactant is going to have to be a compound to break apart. So just like a synthesis reaction, you recognize it because there's only one product. For a decomposition reaction, you recognize it because there's only one reactant. Now it's called an analysis. To analyze something, you break it apart. And so that's why that's also referred to as an analysis reaction. Okay, let's look at an example. So again, you can recognize it's an analysis reaction because there's only one reactant. So you can stop the video right now and I bet you could write a balanced equation here. You just need to break it apart. Well, what's it made up of? It's made up of hydrogen and oxygen. Okay, so let's look at this reaction before we actually do it.
The decomposition of water is thermodynamically disfavored, but can be made to occur by electrolysis, the application of an external electric current. Here, platinum electrodes transfer electrons between two cell compartments to separate the decomposition products. Gaseous oxygen rises from the anode at the left, hydrogen from the cathode at the right.
Okay, so we have oxygen and hydrogen gas forming. Hydrogen and oxygen, both diatomic gases. And then to balance it, just need to put it 2 in front of the water and 2 in front of the hydrogen. Notice that you make twice as much hydrogen as oxygen. And if you look in the test tubes, this is the hydrogen and this is the oxygen. This is called electrolysis. It's something we just discussed in IB Chem 1. I guess I discussed. Balanced. Okay, now this is regular table sugar, sucrose. Now, before we try to break it apart, you can see it's made up of carbon, hydrogen, and oxygen. Well, you might be tempted to write carbon, hydrogen, and oxygen, but a decomposition reaction need not go exactly into its elements. It might just break apart to form 2 different compounds. In this case, it's going to form an element and a compound. So let's look at the reaction. Now, for the reaction to take place, it needs what's called a catalyst. And for this reaction, sulfuric acid is the catalyst. So what you're going to see in the video here is how they're going to pour some sulfuric acid into some sugar. Now, I do this in class. It takes about 2 minutes for this to take place. They're speeding it up here a little bit. Great deal of heat, and that black substance that's coming off there is just pure carbon, and you can see the steam being given off, and that's the water. So those are the 2 products, carbon and water. To balance it, we just need 12 in front of the carbon and 22 in front, 11 in front of the water. Okay, so why don't you try this one? So it's mercury 2 oxide. So see if you can write a balanced equation for it. Stop the video. All right, so let's take a look. We know that bromine is a liquid and oxygen is a diatomic gas. And then to balance the reaction, we need to have 2 here to balance the oxygens and a 2 here to balance the mercury. Let's see this reaction.
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, The decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
Okay, next, single replacement reactions. An element replaces another element in a compound. Okay, so in this case, you can see that the element A by itself is going to take the place of B and become part of the compound. It's kind of like, to say in class, it's like you're out on a date and you bring your friend along, and after later on that night, things didn't go the way you had planned, and now you're all by yourself. Okay, so let's look at an example. Oh, for single replacement reactions, there's two types. Cationic, the element is a metal. So the element meaning that element that's by itself. So here, an element in a compound. So the element is a metal. Or anionic, the element is a halogen. So like if this was, say, chlorine or bromine or iodine. So we'll look at a couple examples here. Okay, cationic. And I'll explain why we call it cationic in a second here. If you were to take copper and to put it in a solution of silver nitrate, you would form silver metal, and the solution would become copper 2 nitrate. To balance it, 2 in front of each of the silver nitrate and the silver. Okay. Now, why is it called cationic? Because silver is a positive ion. Copper is a positive ion. Remember, positive ions are cations. So single replacement, it's the metal replaces a cation. Let's look at this reaction. I'm going to have to fast forward this as it takes so long. Now this lab you actually would have done in class, sorry. You just take some copper metal and put it into a solution of silver nitrate. And slowly you can see silver crystals forming on the copper metal as the reaction above there is taking place. It's really, really quite pretty. Sparkly silver crystals. Now notice that the solution is turning blue. Here, no color. Now it's blue. And it's blue because copper nitrate is a blue solution. Copper solutions have a characteristic blue color. Okay, let's look at another cationic. Magnesium into hydrochloric acid. Well, that's going to, when you put magnesium into hydrochloric acid, it's going to start to fizz. Bubbles will be given off, and that's hydrogen gas is being produced. So to balance it, you need a 2. Okay, now why cationic? Well, hydrogen is a positive ion. The magnesium is a positive ion. Those are cations. So the metal replaces the cation and becomes a cation. Let's look at this reaction.
When we put magnesium metal into aqueous hydrochloric acid, the two react. Aqueous magnesium chloride is formed along with gaseous hydrogen.
Okay, now remember there's two types, cationic, and then there's also anionic. So in this case, we're going to take chlorine and put it into a solution of sodium bromide. And what will happen is that elemental bromine will form and chlorine will become part of the compound. Balancing it. Now, bromine is a negative ion. Chloride is a negative ion. Those are anions. So the halogen replaces another halogen in the solution, and they're both anions, negatively charged. So that's why it's called anionic. You only need to understand this will be the case for halogens. So there's only 4 halogens: fluorine, chlorine, bromine, and iodine. So anytime you see one of those 4 as the element by itself, that's what's going to happen. Okay, so now this reaction isn't terribly interesting. Let me point a couple of things out here. Chlorine is a gas, but just like all gases, it's somewhat soluble in water. Like carbon dioxide in water is what gives sparkling water its fizz. So what you have here is chlorine, what we call chlorine water. So you have chlorine gas dissolved in the chlorine water, in water. And they're going to pour that into a solution of sodium bromide. That's what we have over here. It has no color. Now, when that happens, bromine will form, and bromine, as you saw earlier, has that distinctive kind of orange-brown color. So you'll see that forming here. And just like chlorine is a gas, it's soluble, it's slightly soluble in water, so is bromine. It's a liquid, but it's soluble in water. This would be called bromine water. Not aqueous bromine, because it's not where it's dissolved. It's well dissolved, like a sodium, like an ionic compound would be dissolved. It's bromine water. Okay, and then double replacement reactions. For a double replacement reaction, anions and cations in 2 compounds replace one another. They switch partners. Okay. So the A and B trade partners. So it's kind of like going out on a double date, and you can kind of guess where that's going to go. There are 2 types of double replacement reactions. A precipitation reaction, where one product is a solid. Now you saw that in, remember the lab naming precipitates? Each time that you mix together the 2 solutions and you saw a color change taking place, that was a solid that formed. If you were to evaporate the water, it would be a solid. And then there's also what are called neutralization reactions. And that's when an acid and a base react to form an ionic compound and water. All right, let's do an example, or look at some examples. Okay, so first, precipitation. So this is lead 2 nitrate is going to be mixed with potassium iodide. They're both aqueous solutions.
When a solution containing iodide ions is added to one containing lead 2 plus ions, a precipitate of lead iodide forms. This precipitation reaction occurs because lead iodide is an insoluble ionic compound.
Okay, so the yellow color that you see here is the lead 2 iodide. That's our precipitate, the solid. And then the potassium and the nitrate, that remains aqueous. Okay, then to balance the equation, we just need to put a 2 there. Oh no, and we also need to put a 2 here. Precipitation makes a solid. Okay, now this is a neutralization reaction. It's still double replacement, but in this case, you're going to make an ionic compound and water. Now, what distinguishes a neutralization reaction, or how you recognize it, is it's an acid reacting with a base. Now, all you need to know about what a base is that it contains the hydroxide ion. So sodium hydroxide, potassium hydroxide, calcium hydroxide. If it has hydroxide in it, it's a base. So when this reaction takes place, you form an ionic compound, so the sodium and the chloride, and then the hydrogen ions and the hydroxide ions form water. You might be tempted to draw it like that, HOH, but it's water. Okay, now this reaction, you can't see anything taking place. Acids don't have a color, bases don't have a color. When you mix it together, you're not going to see anything happen, but it gives off heat. It's what's called an exothermic reaction. It gives off heat. So if you were to put a thermometer in a beaker where this reaction is taking place, the temperature would go up. If we were at school, you would be doing this lab, and you would fill the test tube, and you would see that the test tube is getting warm. Okay, and last, a combustion reaction. Okay, burning. Okay, for a combustion reaction, a substance reacts with oxygen to produce heat and light. So it's a burning or an explosion. Oxygen has to be one of the reactants. So for something to undergo a combustion reaction, oxygen has to be present. So reactant, oxygen to form products, whatever the products might be. Now it also produces heat and light, as we said, but we wouldn't include that in our chemical equation. That's just kind of FYI. If the reactant is what's called a hydrocarbon, you always have the same two products. A hydrocarbon, as the name implies, it's made up of only hydrogen and carbon. When it burns, it forms carbon dioxide, gaseous carbon dioxide, and liquid water. Okay. You only need to know this type for a combustion reaction. You can have other reactants and other products forming that are combustion reactions, but you don't need to worry about those. This will be the only type you need to be able to classify as a combustion reaction. If it's a hydrocarbon and oxygen, it's a combustion reaction, and the products will always be carbon dioxide and water. So all you need to do is look at the hydrocarbon, what are the subscripts, the X and Y here, in order to balance the equation. Okay, so let's look at an example. Okay, so this is methane, just natural gas and oxygen. And this is what's taking place when we light Bunsen burners. Methane is burning. The products, of course, are carbon dioxide and water. So all we need to do is balance it. So 2 in front of the water and a 2 in front of the oxygen. Let's do another one. This is ethanol and oxygen. So see if you can stop the video, see if you can write a balanced equation for it. Okay.
Here, whoosh bottle.
Oops. Okay, yeah, this is called a whoosh bottle. What they've done is they've taken some ethanol and put it into this 5-gallon water bottle, and just kind of swished it around, just a very small amount, swished it around a little bit so that it mostly vaporized. So you have ethanol vapor in there. And then when you drop a match in, this is what happens.
Here, whoosh bottle.
Pretty cool, huh? One more time.
Here, whoosh bottle.
As cool as that was, all it is burning ethanol. And our balanced equation, and that would be it. Okay, now let's summarize this. Classifying reactions. So there's 5 types: synthesis, analysis, single replacement, which has 2 types, cationic and anionic, double replacement, which has precipitation or neutralization, and then combustion. Remember, combustion, you only need to know the burning of a hydrocarbon to form water, carbon dioxide and water. Okay, now, these are just 5 basic types of chemical reactions. However, there are many, many, many other classifications. So let me give you an example. You don't need to copy this down. I just thought I'd show you this. Kind of cool. Okay, this is called an oxidation reduction reaction. And what they're going to do is drop a penny into nitric acid. Now, pennies after 1982 were made mostly of zinc, and they have copper coating. But prior to that, they were just pure copper. And so what they're going to do is going to drop one of those pennies pre-1982 into nitric acid. And this is what happens. And the brown gas that's being given off, nasty stuff, as they'll say. If you see, whenever you see a smoggy city, that brown smog, it's nitrogen dioxide. Okay, so this reaction, if you were to look at it, it doesn't fit any of those categories that we just talked about. You might want to think, well, it's like a double replacement or a single replacement. The copper has taken the place of the hydrogen to form the copper-2 nitrate, but we don't have hydrogen gas. So it doesn't fit any of those categories. So the 5 types that you've just learned are just 5 relatively simple, basic types of chemical reactions.